Alright, so for this next one, we're going to look at greatest common factor, least common multiple, dimensional analysis, and ratios, proportions, and percents to kind of translating between the three. These are just some one-offs that I wanted to cover, so we're going to do them all together. The greatest common factor, we're going to say of these two numbers, m and n, defines the biggest common factor of m and n. So let's look at 18 and 12, for example. 18 can be broken down into its primes as 2 times 3 squared, and 12 can be broken down as 2 squared times 3. So our next step then is to find the largest power of each prime between the two of them that they share. So we need whatever primes they share, and we take the greatest power that is or we take the one that's the same, and multiply them together. So we have 2 squared in 12, but we only have a 2 to the 1 in 18, so we can only take a 2 to the 1. We have 3 squared in 18, but we only have a 3 to the 1 in 12, so we can only take a 3. If there was 3 squared in both, we could have taken a 3 squared. So we get 2 times 3, which equals 6. So that's the greatest common factor. For least common multiple of m and n, it defines the smallest common point of m and n. So an example of this is 36 and 48. 36 can be broken down into 2 squared times 3 squared, and 48 can be broken down into 2 to the 4th times 3 to the 1. We find the largest power prime numbers from m and n and multiply all of them together. Notice in this one, we don't care if one has one and the other doesn't, or if one has the same prime but it's to a greater power. We want, out of every number being considered, the prime with the largest power, each instance of that. So between the two of them, the highest power of 3 is 2, and the highest power of 2 is 4. And there's no other primes available for us to pick. 3 squared times 2 to the 4 is 144. So if we kept adding those numbers together, the point at which they would meet first would be 144. For the greatest common factor and least common multiple relationship, that is m times n is equal to GCF, or greatest common factor, times least common multiple. An example would be m is 18 and n is 12. The greatest common factor of 18 and 12 is 6. We found that earlier. The least common multiple of 18 and 12, so we can break 18 down into 2 to the 1 times 3 squared, and we can break 12 down into 2 squared times 3 to the 1. The biggest power for each prime available to us, that would be 3 squared, and 2 squared multiplied gives us 36. Now we plug everything into check for our relationship. So m times n, 18 times 12, and greatest common factor times least common multiple, 6 times 36, and we see that, yes, that does work. 216 equals 216. Next, we're going to go to dimensional analysis. You're going to see this with like weight, with time, anything like that. It's used a lot in science classes. But we multiply the unit fractions to receive an answer in a desired unit. So, for example, if I wanted to convert 1 hour to seconds, I would have 1 hour over 1 times 60 minutes over 1 hour times 60 seconds over 1 minute. So the fraction right here, 60 minutes to 1 hour, that's 1 over 1. So that's fine to multiply by. And 60 seconds over 1 minute, that's also 1 over 1. It's just different units. And as we multiply across, the hours will cross, right? We have an hour in the numerator, an hour in the denominator. That'll cross. Minutes in the numerator, minutes in the denominator. That will cross. And then all we'll have is ones across the denominator, and we'll have 1 times 60 times 60 seconds, which will leave us with 3,600 seconds, which is the correct answer. Next, let's go to ratios, proportions, and percent. So what I'm concerned with here is translating between the two and making sure you guys understand what you're finding. What I found is that people make mistakes because they're not viewing it from the right perspective. So let's look at an example. There are 3 girls for every 4 boys. That could be 3 to 4, 3 to 4 again. I mean, just rephrase 3 over 4, 0.75, or 75%. We could also have 3 to 7. This is also 3 to 7, 3 over 7, 0.43, or 43%. Neither one of these is wrong. They're just looking at this problem and expressing it differently. The first one is saying girls to boys, right? And the second one is looking at girls to the total number of people, right? So if there's 3 girls for every 4 boys, then it's 3 girls for every set of human beings, if you want to say that. And in this example, it's fairly obvious, but on the praxis, they may purposely word problems strangely in order to trick you into this kind of a scenario. So be aware of it and watch out for it. And that's it for this one.